And
it's sort of like the Wile E. Coyote model. You know, you can run a little bit past the edge of the cliff, and it's actually okay.
That's right. Indeed. And so we talked to a whole bunch of users and system administrators about that, and to a person, is from the conversations I had, they're like, yeah, close enough is fine, just give it to me per user. And of course, then the question is, what's a user? And so what we're able to do is we're able to track this, not only using standard POSIX UIDs and GIDs, but also CIFs or SMB SIDs, which can be these monstrous, ginormous things. It actually all works.
Things like that.
Indeed. Yep, so there are several new properties that come along with this, and again, these properties are on a per file system basis, where you can say that you have you can send user quota or a group quota. You can get statistics on how much space is a given user or group using in a particular file system. And the interface for doing that is just like any other properties in ZFS. It's through the get set interface of the ZFS command. And the user group can be specified in a very natural way. It can be numeric for either the UID, GID, or SID, which will always work. Or if you have name service up and running, we can do the mapping for you as well. We'll map whatever POSIX or SID name you give us to its actual UID or SID, and then write that in and keep track of it that way. And again, you can sort of see an example of the output here for a file system we were playing around with. And it tells you what kind of entity is being tracked, whether it's a POSIX user or group or an SMB user, what its name is, and again, if name service isn't running, you'll just get a bunch of numbers back there, and how much they've used and what's their quota. So it's a very natural interface in that regard. Try to make it consistent with everything else in ZFS.
So, pool recovery. So the problem that we have here is we, in general in ZFS, assume that the hardware that we're dealing with is not necessarily super reliable. We assume that disks can fail, that computers can fail.
But we do assume that they don't outright lie to us.
Right, so if we say, for example, here's the following series of IOs, and then I need you to do a write barrier before you do the next IO. Write barriers are one thing that we actually really do depend on for correctness, because otherwise what you can end up doing, if you think about if you have a tree of blocks, and you write out all the new leaves of the tree and bend the new root, things are good. If you write out the new root, but the leaves haven't been written yet, then the root points to stuff that is still garbage on disk, and you have really a catastrophically destroyed pool. So the sequence of events that can happen here, ZFS sends synchronized cache command off to the disk throws it away, way to go disk drive, and it doesn't even tell us that it did it.
As a matter of fact, it tells us that it did do it, which is the worst thing.
Yeah. So you might wonder, well, why don't people see this all the time? And it's because there are two ends of the spectrum where you'll never see this problem. At the high end, you'll never see it because you're never going to have disk drives or bridges that blow off synchronized cache commands. That just, it's not going to be, in any of the hardware that we build, you're never going to see that. At the low end, something like a laptop, you'll never see it either for a completely different reason, which is that a laptop never loses power because it's got a battery built in. So the idea that, oh, I yanked the power cord and suddenly things died, you just don't have that failure mode in laptops. Where we do see it, and it comes up on ZFS Discuss if you follow it, is people doing their own do-it-yourself home storage systems where they've got some little PC, they get a bunch of USB drives, plug them in, and then experience this event in response to power failure.
And this is actually something we've talked to Apple about, and they have the exact same problems. A lot of FireWire or USB to disk drive bridge chips. They pass through read, they pass through write. Sometimes they pass through the inquiry command. Other than that, they silently drop everything and report back, yep, we're good. So synchronized cache being one of those that gives a short shrift there, and that's especially where we see this.
Yep. So the fix to this is what we want to be able to do is to recover a pool, even in the case where devices have ignored write barriers that we rely on for correctness. But what we do is we take advantage of just a very simple fact, which is that, remember, the purpose of the write barrier is to make sure that if I send out 10 writes to nodes of a tree, then the 11th write is the root of that tree. What I really need, well, ideally, I want the 10 to go out, and then once I know those are committed, then I want the 11. But really, I'm in a consistent state whenever those 11 writes are done, right? Even if they weren't done in order. And each time we push out a transaction group, there's a whole collection of writes that goes out like that. So even if the most recent transaction group got corrupted because the disks didn't honor write ordering, chances are quite good that the previous transaction group, that all the writes that comprised it, have long since made it to disk, because that was several seconds ago. So what we can do, because we actually have a ring of Uber blocks that allows us to look backward in time, we can say, if the most recent Uber block, I do a scrub of just the most recent transaction, which we can do in a very short amount of time, a quarter of seconds. If you look down there and say, this stuff doesn't checksum, then we can go back to an earlier Uber block and say, let me try that out. Does that all checksum? And in fact, this has been available in the field for a while. Victor Latushkin, he was the one who did the original thing, right?
Yep.
Hacked up ZDB to make an option where it would allow you to basically force the pool to open with a particular transaction group. What this project does is formalize that to where you don't have to be hacking around in MDB or ZDB and doing things like that. And the other component to it is to make it reliable. We ensure that for the previous couple of transaction groups, any blocks that are free, we don't reallocate those until a couple of transaction groups later. The reason we want to do that is because if you want the ability to roll back, the one thing you have to be able to assume is that the stuff you're rolling back to hasn't been stepped on. So if it was free and then immediately reallocated and overwritten, you would lose the previous state if you wanted. So we actually have all this code working, and all we're doing now is sort of finalizing the user experience, things like having the pool go into faulted mode and how we report the status, that sort of thing.
Yep, because we could make it all automatic, but when bad stuff like this happens, generally speaking, the last thing you want us to do is say, oh, this one block of this one file you don't give a crap about, didn't checksum, therefore we're throwing away everything else in that same transaction that you probably do care about. And we just don't want the loss of data to be an automatic, non-user reviewed policy.
Right.
So, triple parity RAID Z. So double parity is, just what you would imagine. You have, some number of data drives and then two so-called parity drives, even though that's not simply parity, there's a little more math that goes into it. The idea is that you can, out of these, 7 drives in my example here, you could lose any 2 of them and still, through this complicated math, be able to recover the original data. So triple parity just takes that up one more, which is, assume that I have, 3 plus 5, let's say, is I lose any 2 drives, and I still have enough data to recover any spurious errors that I have. And what this allows us to have is to have disks that have a higher bit error rate, or BER in this case, to survive in a case where other drives that are in the same stripe have completely failed. So we've actually talked to a few disk drive manufacturers about something like this, is can you give us a disk drive that is higher capacity, slightly less reliable, and have that be something that we can choose as an option. And they've said, yeah, we can do that. There are actually formatting options that the drives can do that dictate how much error recovery information they have on a per sector basis. And it turns out it's actually, you can get a lot higher capacity by just saying, it's okay if these drives can't recover each and every read. ZFS has more information available to it than a single disk drive does. We'll take care of the recovery. You just store more information for us. And because what this does is, you have some number of sectors and some error recovery information on the disk drive. If you're using less error recovery information, that means for a given sort of arc radius of information on the disk, you store more information, which not only is more information, but it's actually higher performance because the disk drive still spins at the same speed. You just have more readable data flying underneath the head within a given time. So again, as I mentioned before, Adam Leventhal is the guy that wrote this code. He's actually got it working, and he was threatening to put back. Did he actually put back yet?
I checked last night. It was not indicated yet, but as I say at the end, it could be integrated before we're done talking.
Yeah, indeed.
I didn't see it this morning.